Okay, so we are at the point in the year where we're going to talk about carbonyl chemistry, which is the most important chemistry for going on to talk about biochemistry and also has a lot of questions. The ACS final exam has a lot of questions on carbonyl chemistry, which is unfortunate because we always get to it in the last part and it always feels rushed. And it might not be any different this time, so I should probably shut up and start talking about carbonyls. But what I'm going to do is I'm going to kind of lay out our grouping. So in terms of the carbonyl chemistry, there's two distinctly different groups that we're going to talk about. And the first ones that we're going to talk about are the aldehydes and the ketones. And I always assume there's an R group on one side. So this is our aldehyde and this is our ketone. So I'm going to group those together, and every book does as well. And at some point somebody said, well, hey, if carbonyl chemistry is so important, why don't we go over it earlier in the semester? And I think the answer is because nobody writes a book that way. But we're going to kind of fuse everything together in terms of why we're going to group these the way that we are. So with an aldehyde and a ketone, they go together in one chapter, and then the carboxylic acid and molecules that are related to it called derivatives all come in the next chapter. So it's going to be carboxylic acid chlorides that we've talked about a little bit. It's going to be carboxylic acid anhydrides. So this is an anhydride. This is obviously the carboxylic acid chloride. We have the esters, and then finally our amides. And so that's the way we group them. These are all called carboxylic acid derivatives. And the reason that they're called carboxylic acid derivatives is that when they react with either H plus H2O or hydroxide and H2O, they basically make a carboxylic acid. And there'll be one other molecule in this carboxylic acid derivatives as well that is kind of an oddball, but it's the nitrile. So all of those groups, when they're reacted with acid and water or base and water, they get converted to a carboxylic acid. And this process is called hydrolysis. That's the hydrolysis process. So this is how we set up the next few chapters. And then we'll finally have amines to talk about, and then also esters. Well, then what's called Aldol condensations and other reactions that we'll get to like the last couple days. So this is what we're gonna talk about. So the reason that these groups are the way they're organized this way is it's based totally on the leaving groupability of the group attached to the carbonyl. On one side we'll have an alkyl group, and then on the other side we'll have this, what I call Y group. And so if you think about adding a nucleophile to this, And our nucleophile, let's start with a negative nucleophile. We've already done this reaction before. This nucleophile could be H minus, or it could be R minus, right? It could be a Grignard, could be a reduction. That comes in, attacks the carbonyl, and the pair of electrons goes up so that we form our O minus, and then we've added our nucleophile. And then what tries to happen here? So we try and reform the carbonyl by bringing this pair of electrons down. Now, if this nucleophile is either an alkyl group or a hydrogen, can it leave? No. Right? Alkyl groups, carbon and hydrogen, are the strongest bases that we have, and therefore they are the worst leaving groups. So all that could leave is the Y group. And if the Y group is an R or an H group, then what happens? The molecule just gets stuck there as an alkoxide, and you wait for H plus to come in and protonate it. And that was all the reductions and all of the Grignards that we did with aldehydes and ketones. When we started doing things with an acid chloride or with the esters, things got a little bit different, if you go back and remember that. So this is just simply an addition reaction. But what we're going to talk about now is we're going to take our molecule and we're going to have Y have the ability to leave. Or potentially it could leave. So that now if I took my nucleophile and it comes in and does that first step in attacking, I'm going to end up with my O minus, my Y group, and my nucleophile. And I guess we're not going to do this immediately, but we have done this when we talk about taking something like a Grignard, when we took a Grignard and we reacted it with a carboxylic acid chloride. What happened in that case? And we always had two Grignards. So it would add twice, and so we'd end up with a tertiary alcohol. So what would happen is the first CH3 minus would come in, add to that. So we would end up with our C, with our O minus. Now the O minus tries to make a carbonyl, and can it? Can I bring this pair of electrons back down? Yes, because the chlorine can leave, because there's a leaving group there. So then I lose the chloride, and I ended up reforming or not reforming, but forming the ketone. And then we always had a second equivalent so that it could come in, and we could end up with we would end up adding two equivalents of the Grignard. Now that alkoxide is in a position where I can't bring the pair of electrons back down because I have no leaving group, and so it just basically is stuck, and it waits for the acid to be added so that I can get my final alcohol product. So this would be what is called a substitution reaction, at least this first step, in terms of substituting a methyl group for the chloride. Up to this point, that's going to be substitution. So the way that we're going to talk about carbonyl chemistry then is going to depend on what's the Y group and what's the nucleophile. Because if the Y group can leave, I can get substitution. If the Y group can't leave, then I'm going to get addition. And so this reaction that we talked about as kind of being an odd or an exception to the Grignard reactions, we're going to do a lot of that with the carboxylic acids and their derivatives. And when we have a situation where we have the nucleophile having added to the carbonyl, when this pair of electrons comes back down, we haven't dealt with the situation yet of what if the nucleophile can leave? So we're going to be in situations where the Y group could leave or the nucleophile could leave. And if the nucleophile is a better leaving group than Y, what happens? I just go backwards. Or I get an equilibrium. If the Y group is a better leaving group, then I'm going to end up, bless you, doing substitution. So that's going to be a little bit more of what we do with the carboxylic acids and derivatives. Although when we start here, you're going to see that I basically am going to have equilibria reactions where the nucleophile could potentially leave. Okay, so that's a long-winded way of setting up the next, I don't know how many lectures. A lot. Okay, so we're going to take these one at a time, and we're going to start with aldehydes and ketones and the reactions of aldehydes and ketones. Okay. And I haven't updated the website. I haven't put today's folder in with the reading assignment. And I obviously haven't set the date for whatever chapter we're in, which is the next one on aldehydes and ketones. I'll do that today. I'm behind. You don't see any exams here because they're on my desk. That's as far as they made it. So if you're going to ask, like, what score did I get, it's going to be 5 points less than before you asked. So don't ask yet. This is going to be a rough week. I can already tell. So with our aldehydes and our ketones, then, we can't substitute because these guys aren't leaving. But I already know how to add H minus, and I already know how to add R minus as my nucleophiles, because these were Grignards and those were reductions. But I have a lot more nucleophiles that I can use. Okay. So let's talk about aldehydes and ketones and their reactions. So it's going to be kind of strange, but I'm going to want to take an aldehyde, and I'm going to want to add an alcohol and water to it. Now you might say, how about hydroxide, or how about an alkoxide? Not in this chapter. It's going to take us a few chapters to work our way to that. So I'm only going to react neutral nucleophiles with my aldehydes and ketones to begin with. Okay. And that's because if I use an alkoxide, something completely different is going to happen. So when I decide to use my neutral nucleophiles and react them with aldehydes and ketones, the problem is those nucleophiles aren't strong enough to add to the carbonyl. So the carbonyl needs help. And it's going to get help because I'm going to add H plus to it to begin with. So the reactions that I'm going to do are H plus and an alcohol, or H plus and water. So when I add H plus to this, what should be the first step in the mechanism? Protonate the oxygen. So I'm going to protonate the carbonyl oxygen. Okay, and my arrow goes like that. Now, I'm going to use equilibrium arrows for all of this because the H plus could come back off the carbonyl. But when I do that, I'm going to protonate the oxygen, and I'm going to end up with that oxonium ion. Now, how does the acid help the neutral nucleophile add to the carbonyl carbon? Because there's a resonance structure that I can draw if I take this pair of electrons and give it to that oxygen so that the oxygen doesn't have a charge, but the carbon does. And of course, we know that neither of these two is the real structure. The real structure of this is the resonance hybrid. And so in the resonance hybrid, what I'm going to end up with is that structure. And so what I've done is, when I've given this molecule a +1 charge, a lot of that +1 charge is not going to be, it doesn't want to be on the oxygen, it wants to be on the carbon. And so now I've made this carbon more electron poor, which is going to make it more attractive for the water to now come in and add to, or the alcohol. So by adding H plus to this, what I've done is I've made the carbon more electrophilic. And it's kind of strange because I'm adding it to the oxygen, but I'm increasing the delta plus charge on the carbon. So that's our first step. We're going to add H plus. We're going to end up with these two resonance hybrids. It doesn't matter which one you add to. So I'm going to write both of them again down here. And then what I'm going to do is I'm going to add water to each one of these carbons. So the water is going to come in, and if it adds to this resonance structure, it'll add to that carbon, and then that pair of electrons will go to the oxygen. If the water comes in and adds to the carbocation, just adds a carbocation. So I don't care which one of these two resonance structures you use, but you're going to have to use one. So then what happens is we end up with, in each case, I'm going to end up with that. So in both cases, I'm going to end up with that oxonium ion. And what's that oxonium ion going to do? And I, again, should probably put equilibrium arrows here because the water can add, or the water could leave. And so now I'm going to end up with, when I lose my H plus, I'm going to end up with this. So it doesn't matter whether this is an aldehyde or a ketone. In other words, up here, I could go through this entire molecule and say it doesn't matter whether this was an H or whether it was an R group. And that's how I indicate the H or the R, by putting one of them in parentheses. Aldehydes, ketones both react with water to form this molecule, which is what's called a hydrate. So that's the mechanism for making this hydrate. Now, at this point, we have to talk, well, at this point, I should say, is there anything, any questions, anything that doesn't make sense in terms of that mechanism? And you're going to get lots of opportunities to practice this mechanism, both for points and for your own self-practice. So this is an equilibrium reaction. And the question is, where does the equilibrium lie? And the equilibrium, so if I rewrite this reaction over here of ketone or aldehyde plus H2O, I'm going to put the H plus now over the arrows because the H plus is a catalyst. And I'm going to form my hydrate. The equilibrium for this reaction lies mostly on the left. The equilibrium lies on the left for most molecules. So if you take a run-of-the-mill aldehyde and you throw it in water, or you throw it in water with acid, there's only going to be a little bit of the hydrate that's formed. Most of it's going to lie unreacted. Now there are exceptions to this, but the exceptions would be, how would I push the equilibrium to the right? And so if I'm going to push the equilibrium to the right, I have to think about, well, how have we pushed equilibria to the right in the past? What could you use? Jacob?
Changing temperature.
Temperature establishes a new one, but temperature really won't push right or left. Why?
More reactant.
So I could add more reactant, which would be sort of using Le Chatelier's principle, except in this case, the water here is normally water's normally the solvent, so I'm basically at my maximum sort of concentration of water. When we had this equilibrium, our acid equilibrium, how did we push the equilibrium to the right?
By making A minus more stable.
By making the conjugate base more stable. So when I made the product more stable, what happened to the equilibrium? It would push to the right. So if I can't use Le Chatelier's principle, and temperature won't change the equilibrium that much, I'm left with making structural changes to try and make the product more stable. So I guess because everybody's kind of looking at me like, well, I don't know, it's Monday morning. It's been a long weekend. Hopefully everybody's bracket, well, I don't know, my bracket got busted yesterday. So if you're thinking about pushing an equilibrium to the right, here's the example we used with the acids. We said that, not R minus, but let's say we had this type of an acid. And maybe I put a methyl group here. So this is a sulfonic acid. And this is a very strong acid. Why was it a strong acid? Because when I write its equilibrium, I end up with this. And this would even be a stronger acid than a carboxylic acid. And a carboxylic acid is an even stronger acid than something like an alcohol. So if I look at these three examples, and we get to stronger acid as we move up these examples, so the sulfonic acid at the top is the strongest acid. Why is that? Because in each one of these cases, going from top to bottom, the conjugated base is more stable. Why is the carboxylic acid, or the carboxylate here, why is this more stable than an alkoxide? Because of what?
Resonance.
Because it has resonance structures. Right? The carboxylic acid has two resonance structures. The more resonance structures you have, the more stable you are. So in this case, more resonance structures, more stable conjugate base, the equilibrium pushes to the right, and you get more H+. The more H+ you get, the stronger the acid. Right? So that's why carboxylic acid is a stronger acid than an alcohol. Let's go up one step. What's making this even more stable? I'll take an answer anytime you want. It's been a while since I've used this. Change to the morning class. Ashton.
There's 3 resonance structures instead of 2.
There's probably even more than that. Because it's in the benzene ring. So the answer is there's a lot more resonance structures. And so with even more resonance structures, what does that do to the conjugate base? It makes it more stable. Even more stable than a carboxylic acid. Okay. So when I go back here and I say, all right, I want to push the equilibrium to the right, one of the principles to do that is make the product more stable. Is that going to work in this case? Sadly not. I can't have a big effect on the product. So then I'm stuck to think backwards and go, okay, well, if I need to make the product more stable, what if I made the reactant more unstable? So could I make this more unstable in order for it to push the equilibrium to the right? And the answer would be yes, I can. But then I have to think how. Well, let me ask a question. Aldehyde or ketone? Which one's more stable? Or which one's more unstable? Let's just deal with stable. Which one's more stable? Emma was never in this class. I should have it announce the name. That's more fun.
Abby Bernard.
More stable is the ketone, yes. This is more stable. You want to offer a why? Or do you want me to spin again?
I think because the water is full.
They're going to do what with the electron density?
Like being solid.
Push it. So every time you have an alkyl group, it's going to push electron density into the carbonyl. The carbonyl likes that. Where have we seen this before? How about a carbon-carbon double bond? What makes a carbon-carbon double bond more stable? More substituents, more substituted. The more substituted the carbon-carbon double bond, the more stable it is. Carbonyls are no different. So an aldehyde is less stable than a ketone. So what would be the most unstable aldehyde I could make? One with
Carbon monoxide.
that's a carbon-oxygen triple bond. So I still want two groups attached here, but I want it to be the most unstable. It's to make it formaldehyde with two H's. That's going to be the most unstable of the aldehydes. Because now I have absolutely no carbon groups to push electron density in. So it turns out that formaldehyde, when you react formaldehyde and water, and if you just, formaldehyde itself is a gas. You'll oftentimes hear of people maybe in a new house, or perhaps some of the new car smell is a little bit of formaldehyde because it's used for plastics and other things. And so sometimes you'll have a little bit of formaldehyde coming out of the construction materials, which isn't good because formaldehyde is probably a little toxic. But if I'm doing this reaction, I don't actually need acid. If I take formaldehyde and I put it in water, it's what's called formalin. And so if you have something dead in a jar, sometimes that jar will contain formalin because it's the preservative. You'll sometimes hear, oh, well, that's in formaldehyde. Technically, it's not in formaldehyde, it's in formalin, which is the formaldehyde liquid. I think in biology it's all in methanol. But there was a time when stuff was in formaldehyde, or formalin. So because that's the most unstable aldehyde, you can push the equilibrium so that the equilibrium lies here, and this is now the major product. So that's one way to push the equilibrium to the right. The other way is to do something like this, which is let's add electron withdrawing groups to the carbon attached to the carbonyl, so that the electron withdrawing groups pull the electron density away from that carbon, which then will pull electron density out of the carbonyl. If a carbonyl is more stable by pushing electron density, it's going to be less stable by pulling electron density out of it. So this is what's called chloral. And it's the classical molecule that when, again, you react this with water, you make what's called chloral hydrate. So you can use this approach of attaching electron withdrawing groups like halogens to the carbon attached to the carbonyl, and it will push the equilibrium to the right. So again, what we're doing is we're making the reactant unstable to push it to the right. Does that kind of make sense? Gotta give me a little feedback, or else I'll push the button and ask. We'll just keep asking. So those are hydrates. A run-of-the-mill aldehyde is not going to form much hydrate. But special ones like formaldehyde or chloral, they will. But we have to do something special to them. What about ketones? Same thing. Run-of-the-mill ketone, not going to form much hydrate. What's the mechanism going to look like for forming a hydrate from a ketone? This mechanism right here that I wrote out, erase the H, put in a second R group. Same mechanism. So, hydrates are the first molecules that we can make by this addition of a weak nucleophile with acid catalyst to a carbonyl. So, all right, great. Let's do an alcohol. Because HOH, probably not that much more different or whatever than ROH. So let's do the same thing. Let's take an aldehyde now and let's react it with an alcohol with now acid as the catalyst. So what's the first step in my mechanism?
Kristen Joggin.
We're going to be waiting for a while. Well, I can take attendance with this thing too.
Joseph Line.
What is the first step?
Move the electron
To where? So the first step is going to be, starts with P. Protonate the oxygen, first step. By doing what you said, which is protonate the oxygen. That's why there's certain things that I've said over and over again. Just all you got to do is repeat them and understand what they mean. Right? Guy I had for high school, or a guy I had for math in high school for a couple of years. That's all he would do. You had to memorize like what his sayings were, and he would just go around and ask. He would drill everybody during the entire period. You couldn't do that now because you'd destroy somebody's self-esteem, but you had to learn it, and that's the easiest way to learn it. So whenever we have an oxygen and acid, protonate the oxygen. Done. Next step. What am I going to do next? Remember, I'm kind of doing the same thing I did before.
Jacob Turbin.
Well, there's a resonance structure for that with the electrons being moved up to the oxygen and the positive charge being put on the carbon.
Okay? I'll accept that as a step. Now what am I going to do with the water? Or with the
Caroline
alcohol?
Maltese.
Well, she's not here either.
Alexanera.
So what do we want to do next? I'll give you a hint. Here's the electrophile and here's the nucleophile. So what did I do in the last mechanism? I had the water attack the carbonyl carbon. So now what do we want to do? We want to have the alcohol attack either one of the carbonyl carbons. If it attacks the one with the plus charge, I'm done. If it attacks the carbon without the plus charge, then that pair of electrons goes up to the O. Okay. So I'm going to have the nucleophile attack the carbonyl. Okay, that's going to be an equilibrium reaction. So in the end, in both those cases, I'm going to end up with this. And what do we have to remember about that? I'm adding the whole alcohol, so I'm going to end up with that oxonium ion. Okay. What's the next step? I got an oxygen with a plus charge. What does that oxygen want to do? Well, I didn't.
It wants to get rid of it.
Right. It wants to get rid of the plus charge, and how's it going to do that? Lose the H plus. I'm going to lose the H plus, and now I'm going to end up with a neutral molecule that looks like this. I've now added an OR group to the carbonyl, and the carbonyl has now become an OH. This mechanism is exactly the same as adding water to an aldehyde or ketone to make the hydrate. It's just instead of having two OHs, I've now got one OH and one OR. Okay, now this compound has a name, and it starts with hemi, which means half. So this is half of what? It's going to depend on whether you react an aldehyde or a ketone. So in this case, this is going to be called a hemiacetal because that molecule came from an aldehyde originally. How do I know that? Because I've got an R and an H. So this is a hemiacetal. If this was two R groups, so it originally came from a ketone, it would be called a hemiketal. So the ketals when we have two R groups, the acetals when we've got an R and an H group attached to that carbon. And that carbon has an OH and an OR. So that's a hemiacetal. Well, if this is half of an acetal, what does a full-blown acetal look like? Instead of having an OH and an OR, it's going to have two ORs. Okay. Now remember, the acid is a catalyst that's floating around. So I could then take, and I'll just start down here, I could then say, great, I'm going to react H plus now with that carbon. And you're going to say, what? Protonate the, I would say protonate the oxygen. And then I was going to say, which one? And then you could say, does it matter? And it always matters. But in this case, if I protonated the OR group, I would go backwards because these are all equilibrium steps. So the only way to go forward is to protonate the OH. That's the only way to move forward. Okay, so I move forward by protonating the OH. And now I make this oxonium ion. What happens next?
The water leaves.
I'm going to lose water. To form a carbocation. What's going to happen next? Something's got to attack that carbocation. What will it be? It'll be alcohol. What if it's water? What if water attacked that carbocation? What would I do? Go backwards. Ouch. Go backwards. But if it's an alcohol, I'm going to move forwards. So now my alcohol comes in. Now I have my oxonium ion again. And what's my final step? Lose the H+. And remember, the H+ is a catalyst, so it's constantly jumping on and off. And if I do that, then I'm going to end up with two OR groups now attached to the same carbon. And again, depending on what this group is, if it's an H, this is now called an acetal. This is the full-blown acetal. And if it's an R group, then it would be called a ketal. So this is the mechanism that I can use, or that I get for forming a hemiacetal as well as an acetal or a ketal. So the whole thing is these mechanisms are kind of tedious, but they're really kind of the same steps over and over again. Protonate something, have it leave, have a new nucleophile come in. And for these systems, then, what we'll do on Wednesday is, okay, where's their equilibrium lie? And I'll let the cat out of the bag, mostly to the left, except in certain circumstances where I can push the equilibrium to the right. And then this type of reaction, you've seen the products of these reactions before in your biology classes. And so I'll show you where do these fit in terms of what are called looking at sugars. And then we'll move on and talk about some of the other things that we can do with aldehydes and ketones in terms of additions. Okay. So we're starting in the next chapter. I think I'm doing this the way I normally do it, which I'm assuming is the way the book does it. So I'll update the folder for today. And if you have any questions, email me or come see me. Or on Wednesday, we'll continue this on. So there won't be anything due for Wednesday. But there will be stuff for Friday.